All right, so I'm live here with 52 weeks of Swift here, and I'm going to be covering extensions, I believe. And I'm going to go ahead and pull this up and see what I got here. So Swift, I'm going to go to the language guide, pull some stuff up here, look at documentation, the language. Here we go. And what do I have next? Extensions. Yeah, that's what I'm going to cover next. And so it's a way of adding functionality to a new or existing class here, including the ability to extend types. And in Swift, with extensions, you can add computed instance properties and computed type properties, instance method type properties, new initializers, subscripts, all kinds of fun stuff. And let's go ahead and share my screen. I'm going to share the playground. There we go. And I'm also going to clean things up a little bit so that it's pretty big. That looks pretty good. Make it a little bit bigger. Perfect. Yeah, got it. Okay, we got Swift playgrounds here. Looks like it's all set up. All right, so to start with the extensions syntax, what does it look like? Well, it looks like this. Extensions, some type, add the new functionality. You can also extend an existing type to make it adopt one or more protocols. So we'll go ahead and throw that in there. There we go. Kind of interesting. So computed properties are really interesting, actually. And I've used this in Python, actually. And I think it's kind of a cool concept, which is you have something where you're doing some runtime calculation, and then you take that and you just add it onto the instance of something. And it really can come in handy for a lot of things, like let's say like an API. I could see how you would want to calculate a lot of different things to give to a user. So here's an example. We have extension, double, we have var, right, immutable variables here, kilometer, meter, centimeter, millimeter, feet. Let 1 inch equal this. So we can go ahead and run all this code, and we see here that let 1 inch is equal to 25. And so essentially what's happening here is that all of these are able to be added inside of here, these computed properties, and we're able to actually take, basically leverage these. And because they're read-only, that's one of the really cool things about it as well. So here's a good example of if I want to go through here and say, let a marathon equal 52.km plus 195. And we can see here that this would be the distance of a marathon, which I've run many of those. And a marathon is, we can actually print this out actually. Let's print a marathon as how many meters. That's pretty cool. It is 42,195 meters. Well, that is a long time. I mean, a 400 meter sprint, I've done a lot of those in my life, is absolutely brutal. And if you think about the fact that this is 42,000 meters long, that's a big difference from just one lap around the track. So initializers here, extensions can add new initializers to existing types, and this enables you to extend other types to accept your own custom types and initializer. And if you add an extension to add an initializer, it doesn't define any custom initializers, you can call that within your extension initializer. So here we go. The example below shows a custom rect structure to represent a geometric rectangle. The example defines two supporting structures, size and point, and both of them have default values of 0.00. So first up, we have a struct here called size. Let's run that. Next up, we have a struct called point. Here we go. Then we have a struct called rectangle, which in fact takes both the point and also the size. And we were able to use those. And it says, because the rect structure provides default values, it receives a default initializer and member-wise initializer automatically. And these can be used to create a new rect instance. And so if we go through here and we want to create, for example, a new rect instance, we can do that. We can say let default rects is equal to rects, make an instance of it. And then we can actually basically fill it out. So if we go through here, we populate this, this will let us make a new member-wise rectangle with the ability to call the origin point and the size inside. And we can actually extend the rect structure to provide an additional initializer that takes a specific center point and size. So that is pretty cool, actually. So if we go ahead and we try this out, you can see that the initial rect here, all it did was tell you the points and then the width and the height. But we're going to extend it right here, and we're going to add in another initializer that again uses point and size, but will have the origin X and the origin Y inside. So let's go ahead and run this. And then we see that the new initializer starts by calculating an appropriate origin point based on the center point and size value. The initializer then calls the structure's automatic member-wise initializer, which then stores the new origin and size values in the appropriate properties. And so we see here how we would actually utilize this. And we can actually make a new center rectangle that again calls rect, but this time notice that it is going to actually put values in for the center. It's going to put values in as well for the size. And so let's go ahead and call this out, right? And now if we actually print this, we should be able to see what's going on. So let's just print center rects, right? And we can see that in fact it is an object with those attributes hidden inside. And then methods, so extensions can also add new instance methods and types to existing types. So that's pretty cool. So basically, this is, I guess, kind of on the road to doing some advanced things with object-oriented programming, like extending a built-in type is definitely pretty cool. So in this case, we're going to make a new instance method called repetitions to int type. Here we go. And this one takes a single argument of type void, which indicates a function has no parameters, it doesn't return a value. After defining this, we could call the repetitions task method on any integer to perform a task that many times. So if we go through here, this is definitely cool. I like this kind of stuff. So if we go through and we say 3 dot, notice now the repetitions comes in. And look, it even auto completes this for us, which is really slick. And so we'll just print hello. I like tricks like this. This is the kind of stuff I like playing around with. If I'm just going to play around with a new language, like I want this kind of stuff. Consecutive statements on line must be separated by, why is it saying that? Oh, I don't need that. There we go. 3 repetitions, print hello, 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 hello. There we go. So that's very, very slick here. You extend it and you say function repetitions task void for underscore. So throw away the loop variable and basically repeat something. Now, we also can do mutating instance methods. So instance methods added with an extension can also mutate the instance itself. and these can modify the self or the properties. And so here's an example of a new mutating method called square. Okay, let's try this out. Go down here, we put in square, so we extend it int, and we say mutating function square. And if we say var some integer, so we make a variable, you can do some int. I see. So you can just essentially add some additional methods directly on type of a built-in type to do fancy stuff. So this definitely is pretty cool, especially if you're into doing like scientific computing or whatever. I can see how you would really want to do this kind of stuff, have custom calculations, whatever it is that you're doing. Some int square. Let's go ahead and run that one more time. Some int square. Well, why is that interesting? So subscripts, extensions can add new subscripts to an existing type. These examples would be another one. And here we go. If we go down here, extension integer, subscript it, and do digit index var decimal base for underscore n0. And so if we run this and we put some, we allow it to do subscripting. Is that what this is doing? Returns 5. Oh, I see. So basically, show me the subscripts. Why does this keep printing every time? Which is kind of interesting. I'm not sure why that. Well, unless I just clear all this out. Let's try that. Let's just get rid of a full screen here, and let's just run just this code and just this code. So it returns back 9. If we go here, this returns back 5, right? So we're able to subscript. And what happens if I want to say -1? What does that do? It doesn't. It doesn't work because they have to be positive subscripts. It's 9. And if we go to 8, it gets us to the end. So we can only go, I guess, this code doesn't have the logic to go negative subscripts, but still very interesting. Extensions can also add a nested type to existing structure. So if you want to do enum kind, positive or negative, well, that's pretty cool. We can also do this, integer case -0 positive. There we go. We go ahead and we add this, and now the nested enumeration can be used with anything, and we can basically print out. And if we build out a more complex example here that use this, we could basically print out like whether something's positive or negative. So I could see actually many real world cases for this. And if we just put a bunch of numbers together, and we try it out, there we go, plus -0. So very cool stuff here. I definitely could see myself using some of these advanced object-oriented programming features, like the ability to add things to built-in types, and definitely cool stuff to be able to play around with. And that's probably all I'm going to cover for today. Next week, I'm going to cover protocols, which are blueprint of methods, properties, and other requirements. So we'll see you next